here comes that message again. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are 2 different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. All right, so we're going to pick up with finishing up chapter 8 from yesterday and then going into chapter 9. Before I start, do any of you have any questions about anything we've done so far? Anything? Okay, well then we'll go ahead and take a look at section 8.9, which is variation. And there are 3 types of variation that we looked at. The first one is called direct variation. It is typically in the form y equals kx, where x and y go up together. If one goes up, the other goes up. If one goes down, the other goes down. K is the variation constant. And let's see here. Here's an example. It says the property tax in a certain county varies directly as assessed valuation. If a tax of $1,575 is charged on a single-family home assessed at $90,000, determine the property tax on an apartment complex assessed at $312,000. Okay, so property tax varies directly as assessed valuation. Let's let P equal property tax and A equal assessed, let's see here, assessed valuation. Okay, so the property tax varies directly as the assessed valuation. Recall K, the variation constant, is always present in these formulas, often not even mentioned. So it says, if a tax of $1,575, that's P, is charged on a single family home assessed at $90,000. So that will allow us to determine K by dividing both sides by $90,000. So K equals, let's see, if we take 1575 divided by 90,000, does it come out exact? It does. It comes out 0.0175. You don't want to round K off. So if it doesn't come out to an exact number, leave it as a fraction and reduce it. Okay, so now I've got P equals 0.0175 times A. Okay, because we put K in here. Okay, now the follow-up question says, determine the property tax, so that's P, on an apartment complex assessed at $312,000. So we take our variation constant times 312,000. So that times 312,000, and we get $5,460 would be the property tax. Any questions about that one? So that's an example of direct variation. All right, next we have inverse variation. Y equals K over X. K is still there, present on top. X is in the denominator. In this case, as X goes down, Y goes up. As X goes up, Y goes down. So there's inverse variation. This says for a fixed voltage, the current in an electrical circuit varies inversely as the resistance in the circuit. If a certain circuit has a current of 2.5 amps, when the resistance is 150 ohms, find the current in the circuit when the resistance is doubled. Okay, for a fixed voltage, the current varies. Okay, so we're going to let C equal current. inversely as the resistance, and R is going to be the resistance. Okay, it says the current varies inversely as the resistance. So C equals K over R. If a certain circuit has a current of 2.5 amps, and I'm going to change that to 2.5. When the resistance is 150 ohms, so we've got that. Find the current in the circuit when the resistance is doubled. Okay, so first of all, we've got 2.5 equals K over 150. We'll multiply both sides by 150 in order to determine what the variation constant is. So 150 times 2.5 is 375. So now we've got C equals 375 over R. Okay, we put that in there. It says, find the current in the circuit if the resistance is doubled. Well, the resistance was 150 ohms, so now it's going to be 300 ohms. And so we get 375 divided by 300. 375 divided by 300. 1.25, and that is amps. Okay, so there's an example of inverse variation. And finally, we have joint variation. Joint variation. In joint variation, we have more than one variable on the right side of the equation, along with variation constant. It says, assume that y varies jointly as x and z. So that would basically look like what I've already written. Find the constant of variation, so find k. If x is 24, when y is 3 and z is 4. So 3 equals, let's see, 96k, 24 times 4, divide by 96, k equals, and let's see, if we take 3 divided by 96, 3 divided by 96, we get a really long, awful decimal, but it's still exact, 03125. Or we could reduce it down by taking 3 over 96 and dividing the top and the bottom both by 3, and we get 1 over 32. So k is 1 over 32, or k is that decimal. All right, with that, we're going to go on to chapter 9. So let's get going here. Yeah, all right. So chapter 9. Section 9.1, we dealt with taking roots with or without using a calculator. For instance, the square root of 49 is 7. And even though 7 squared equals 49 and -7 squared equals 49, when we take the square root of a number, we get what's called the principal square root. And if you take the square root of 49 on your calculator, you get the principal square root. Let's see. On the calculator, let's say we want to find the square root of 340. We find the square root button. Be careful, because there's a square root button and there's an x root button. The square root button you use when the index is an implied 2. The x root button you use if you're taking the third or fourth or fifth root, something besides the second root. So to find the square root of 340 on my calculator, it's a second function. So I push the second function of the x squared button and I get this. And I put in 340, close it up with another parenthesis. Hang on here. Let's see, 340. And I get 18.439088891. And it says round to the nearest 10,000th. This is the 10th, 100th, 1000th, 10,000th place. The 8 would round up, so we get 18.4391 to the nearest 10,000th. All right, then we dealt with variable roots, and we have directions that say assume that all variables are unrestricted, so they could be positive, negative, or 0. So in that case, the square root of 4x squared is 2x, but because when you take an even root, you can't get a negative answer. So because x could be positive or negative, we have to put absolute value bars around it. Let's see, suppose I've got this situation. 81r, or let's see, the square root of 81h to the 4th, that would be 9h squared. Now, again, it says the variable is unrestricted. However, since h is being squared, even if h is negative, a negative times a negative would be a positive. So we don't need absolute value bars there. How about the square root of 36s to the 6th power? Well, that would be 6s cubed. Again, we're taking an even root, so we can't get a negative answer because we don't know whether s is positive or negative, and it's being cubed. It could still be negative, so we need absolute value bars. I might point out this kind of problem. Most people missed that on the Chapter 9 test. They didn't pick up on the fact that they needed to put the absolute value bars around the x or whatever the variable was. So be careful with that. Let's see. Oh, let's talk about domain. We've got f of x equals the square root of x plus 6. Now, you can't take an even root of a negative number. Since this function is asking for the square root, that's an even root of x plus 6. X plus 6 can't be negative. Therefore, it's got to be positive or 0. Solving this inequality, we get that x is greater than or equal to negative 6. So writing the domain in interval notation, it would be bracket negative 6 to infinity with parentheses. Okay. Any questions about that? Okay, let's see here. Find each function value. We've got f of x equals the square root of 3x plus 1, and we're supposed to find f of 8. So that would be the square root of 3 times 8 plus 1, which is the square root of 24 plus 1, which is the square root of 25, which is 5. So f of 8 equals 5. If we were to graph this function, the 0.585 would be an ordered pair, a point on the graph. Let's see here. Let's take a look at some other roots. How about the cube root of negative 27? Now, you can't take an even root of a negative number. And when you take an even root, you can't get a negative answer. But with odd roots, you can take an odd root of a negative number and you can get a negative answer. The cube root of negative 27 is negative 3. Let's see here. The cube root of 125 over 64 is the cube root of 125 over the cube root of 64, which is 5 over 4. Let's see here. How about this? F of x equals the cube root of x minus 3, and it asks for the domain. Okay. Since we're taking an odd root, the radicand, that's the quantity inside the radical, the x minus 3, can be positive or negative or 0. So the domain is going to be all real numbers. Okay. Going to move on. Rational exponents. 9.2. Basically, if we have the nth root of x, that's equal to x to the 1 over n power. The index is the denominator of the exponent. Okay. Let's see here. Let's take this example. We've got 25a to the 8th power, all to the 1/2 power. It says simplify each expression. Assume that the variables can be any real number and use absolute value symbols when necessary. So a product raised to a power, we attach the outside power to each factor inside. So we get 25 to the 1/2 power, a to the 8th to the 1/2 power. 25 to the 1/2 power is 5. A to the 8th to the 1/2 power is a to the 8 times a half, which is 4. Again, even though a could be negative, because it's raised to an even power, a negative or a positive to an even power is still positive. So I don't need absolute value bars there. How about this one? Negative 16q to the 4th, all to the 1/2 power. So that would be negative 16 to the 1/2 power, q to the 4th to the 1/2 power. Well, here we're taking an even root of a negative number, so this is not real. Okay. Let's see here. How about this? 27 to the 2/3 power. Recall that we can rewrite this as 27 squared to the 1/3 power. So we could take 27 and square it, get a huge number, take the cube root of it. Or we could take 27 to the 1/3 power and then square it, which is much easier to do. So it's typically easier to do the root first. The cube root of 27 is 3, and 3 squared is 9. To do this on the calculator, you put in 27, the little caret, parentheses 2 divided by 3, close it up, and that should give you 9. Don't make this mistake. Okay, if you do that, it thinks you're doing this. So you've got to quantify that fraction exponent to tell the calculator what to do. Okay. Let's see here. How about this one? Change each radical into an exponential expression. We've got the 7th root of 7p squared q. So that would be 7p squared q all to the 1/7 power. Going the other direction, let's say we've got 7a squared b cubed to the 1/5 power. Wait a second, that's b squared. And then we're supposed to change that to a radical. That would be the 5th root of 7a squared b squared. So the index and the denominator of the exponent are interchangeable. How about this? 49 to the negative 1/2 power. To deal with a negative exponent, you do the reciprocal of the base and change the sign of the exponent. And 49 to the 1/2 power, the square root of 49 is 7, so we get 1/7. Okay. How about this? 4 to the 2/5 power times 4 to the 2/5 power. Multiplying powers with the same base, you add the exponent. So this would be 4 to the 2/5 plus 2/5 power, which is 4 to the 4/5 power. If we have something like this, x to the 4/3 power times the quantity x to the 2/3 power plus 3x to the 5/3 power minus 4. Distributing, we get x to the 4/3 times x to the 2/3, which is x to the 6/3, or x squared, plus x to the 4/3 times 3x to the 5/3, which is 3x to the 9/3, which is 3x cubed, minus x to the 4/3 times 4, which is 4x to the 4/3 minus 4x to the 4/3. And notice I put that minus sign here instead of over there. And let's see here. This says use rational exponents to simplify each radical. So we're going to take the 6/7 cubed, rewrite it as a rational expression, or excuse me, rewrite it, yeah, using rational exponents. And then this would be 7 to the 1/2 power, which would be the square root of 7. So basically, we're reducing down the exponent in the index. Okay, I'm going to move on from that. And so now we're taking a look at section 9.3, simplifying and combining radical expressions. So if you've got the square root of 28, you're taking a square root, you're looking to unsquare perfect square factors. So I would break this down into squares and leftovers. Then I could say, well, the square root of 4 is 2 on the outside. And so I get 2 square roots of 7. If I have something like this, the cube root of 40, I'm going to take 40 and break it down into cubes and leftovers. 8 is a cube, so the cube root of 8 times 5. The cube root of 8 is 2 outside, and the 5 remains inside. Let's see here. See, I've got this situation, the square root of 147, a to the 5th. Okay. My index is a 2. I'm taking a square root, so I'm looking for squares. 147 is 7 times 21, which is 7 times 7 times 3. So that's 7 squared times 3. So I'm going to write 147 as 7 squared times 3. A to the 5th, I'm going to write it as a to the 4th times a. Recall, I want to have exponents that either match the index or are multiples of the index. The square root of 7 squared is 7 outside. The square root of a to the 4th is a squared outside. And I have the square root of 3a inside. If I have the square root of a fraction, I can break that apart into the square root of the numerator divided by the square root of the denominator. And I can simplify that in this way. Let's see here. I've got a square root over a square root. I can write it as the square root of the radicands and then reduce it if possible and get that. Simplify by combining like radicals. Let's say we've got this situation. And I know I'm going pretty quickly here. If any of you need me to stop, slow down on something, please let me know. So to combine like radicals, we're going to simplify each radical first. 20 could be written as 4 times 5. The square root of 4 is a 2 outside, so I get 2 square roots of 5. 125 is 25 times 5. The square root of 25 is 5 outside, so I get plus 5 square roots of 5. And 80 is 16 times 5. The square root of 16 is 4, so minus 4 square roots of 5. 2 square roots of 5 plus 5 square roots of 5 is 7 square roots of 5. Minus 4 square roots of 5 is 3 square roots of 5. And so there we have simplifying radicals. Okay, let's see. That takes us to 9.5. Solving radical equations. Okay, so let's say we have an equation containing 1 square root. Just like with absolute value equations, we want to isolate the radical. This problem has the square root already isolated. So now we'll come in and we'll square both sides. We'll get x minus 10 equals 1 squared is still 1. Add 10 to both sides. X equals 11. Checking our work. It checks out. Okay. Let's say we've got this problem, the square root of 6x plus 1 minus 5 equals 0. So the first thing we want to do is isolate the radical. So we'll add 5 to both sides of the equation. Then we'll square both sides to get rid of the radical. And we'll subtract 1 from both sides, divide by 6, solve for x, substitute the 4 back inside the radical. We get what the square root of 25 minus 5 is 0. 5 minus 5, 0 equals 0. So that checks. Okay. Let's see here. Let's say we've got something like this. The square root of 3x plus 5 equals 2. So isolating the radical, we subtract 5 from both sides of the equation. Squaring both sides, we get 3x equals 9. Divide by 3x equals 3. But when we check our work, we get 8 equals 2. So this is no solution. Recall this is called an extraneous solution, which is an answer you get by raising both sides of the equation to the same power, but it doesn't work. Also note right here, I had the square root of 3x equals negative 3. A square root can't have a negative answer, so already we know it's not going to work. But if you want to find out what that extraneous solution is, and WebAssign often asks for that, you have to carry it out to get the answer, but then check it to see that it doesn't work. Okay. If you have two radicals in an equation, you want them on separate sides of the equal sign. Squaring both sides, we get that. I'm going to solve for m on the left side, so I get negative m plus 4 equals negative 5. Subtract 4, negative m equals negative 9. Divide by negative 1, m equals 9. Let's see if that checks out. I get the square root of 13 equals the square root of 18 minus 5. The square root of 13 equals the square root of 13. I don't know off the top of my head what the square root of 13 is, but I know that it's real, and the square root of 13 equals the square root of 13. Okay. And we have some formulas. D equals the cube root of the quantity 12v over pi. And we want to solve for v. Well, to get rid of the cube root, we're going to cube both sides. So we get d cubed equals 12v over pi. We're solving for v. So now I'm going to multiply both sides by pi. And then divide by 12. So v equals pi d cubed over 12. Let's see. What about let's see here, this one. 2b plus 29 all to the 1/3 power equals 3. Recall that the 1/3 power is like the cube root. So I could take both sides and cube them. On the left side, the 1/3 and the 3 would reduce down to a 1. So we get 2b plus 29 all to the 1 power, which is 2b plus 29. And on the right side, 3 cubed is 27. Subtract 29 from both sides. 2b equals negative 2. divide by 2, b equals -1. And then let's check our work. 2 times -1 plus 29, 1/3 power equals 3. -2 plus 29 to the 1/3 power equals 3. 27 to the 1/3 power equals 3. 3 equals 3. So it checks. Okay. Right. Let me do it here. Time. Let's see. 9.5. Yeah. Right. So that's it for chapter 9. Tomorrow we'll take a look at chapter 10, and then on Friday, chapter 11. Anything you want me to look at? Any questions about anything before we go for today? All right. Well, then I will go ahead and stop the recording.